Now it is chapter 14. Finite difference methods are traditional numerical methods for solving partial differential equations, PDEs. In this chapter, we'll study those methods for boundary value problems defined on the one-dimensional space. Let's go to the first section. We'll begin with some theory on the boundary value problems. The two-point boundary value problems involve a second-order differential equation in this form. Y double prime is a function of x, y, y prime. X is the independent variable over the interval a to b, and at the left edge point a, the function value is alpha. At the right edge point, the function value is beta. So we call this problem the boundary value problem. Here we have theory for existence and uniqueness. We define d, x is from a to b, and y and minus infinity to infinity, also for y prime minus infinity to infinity. So it is a slab in the three-dimensional space, in x direction is a to b. For the boundary value problem, for here, if the functions f sub y prime are continuous and satisfy these two conditions, then the boundary value problem admits a unique solution. The first condition is f in y-directional slope, f sub y is positive, and f sub y prime is bounded. Then the problem has a unique solution. That's the theory we'll use for solving this example. Show that the following boundary value problem has a unique solution. Let's write down this one in the standard form. Y double prime is, now let's move this to the right side, and minus e to the minus xy and minus sine y prime. Okay, so that is now f. Quite easy to see that this is continuous, and exponential function, sine function combination must be continuous. Now here, consider f sub y derivative. Then from here, minus x will come out from the chain rule, so that x e to the minus xy. Okay. This is positive. X is between 1 and 2, so it's positive, and this one is positive, so that is positive. F sub y prime derivative. Okay, y prime is here, and this will be 0, and minus a sine, and y, derivative must be cosine, right? Okay, sine, derivative of sine is cosine, and y prime. We know that the sine and cosine has a value from minus 1 to 1, so that this is bounded by 1. Okay, so this condition is also satisfied which means that the given problem has a unique solution. It's a simple, right? Among those boundary value problems, we'll consider the linear case. The differential equation is linear if f can be expressed as a linear combination of y and y prime. Look at this equation. Y prime is f. F is a linear combination of y and y prime. Y prime, y, and along with the function of x, p, q, and here function of x, r. So it is a linear combination of y and y prime. Then we call it a linear differential equation. For this linear equation, let's see uniqueness, existence and uniqueness of the solution. Okay, here we have a problem, linear problem, and at left edge point value is alpha, at right edge point the function value is beta, and satisfies these two conditions. P, Q, R are continuous. Then quite easily we can see this whole thing is continuous. Right? Okay. Now here, and also okay, condition over there is that y derivative and y prime derivative are continuous. Now we assume that p, q, r are continuous, then this whole thing is continuous, and then y prime derivative is p of x, y derivative is q. Already we assume p, q, r are continuous, so that eventually the derivatives are continuous, and y derivative must be positive. Y derivative is q, positive. And the final condition, y prime derivative must be bounded. Okay. Now for that one, here f y prime, that one must be p of x. P is continuous on the closed interval. For such a function, it must be bounded. Once a function is continuous over a closed interval, then the function is bounded. So that this one is bounded, so everything is satisfied. So this linear boundary value problem has a unique solution. Now let's try to solve the linear boundary value problem by using the linear shooting method. In the shooting method, we try to solve the problem twice with the initial conditions. For example, we have to get y1 and y2. Now for y1, the function value at the beginning point is alpha. Now its slope, y1 prime at the beginning point, originally is not given. So we assign a value, slope, z1, and solve it. And another solution, y2, at the beginning point, the value is alpha, but now slope is assigned to be z2 and solve it. So it looks like at A, and that's A, and this height is alpha, and we are solving one problem, and along with one slope, and solve another problem with a different slope, like that. So it looks like a shooting from the beginning point. But here, if we reach at B, then this solution will be some value. This solution will have some other value. Now, here, the question is, we have to, for example, beta is here, then now by using these two solutions, we can reach at this beta. That's the idea of the shooting method. In the beginning, we shoot two solutions along with some artificial slopes. Now, we try to make a linear combination of y1 and y2, and in this case, the lambda must be chosen such that y at A is already satisfied, but y at B must be beta. That must be satisfied. We have to find the lambda satisfying such that y should satisfy this condition. Okay. So here, once we start with this linear combination, and at B, we reach this one. Now, we try to solve this equation for lambda. Okay. Then lambda becomes here as far as these are non-zero, the bottom is non-zero, lambda is well defined. So we can find lambda. After finding lambda from this equation, now the solution will be finalized. So its idea is simple. Okay, here we have a claim. This is the theory for the linear boundary value problem. And once we try to use the shooting method, then either y1, y2 are exactly same, so that y can be decided from one of them, y1, or once they are different, then at the last point, the right edge point, the two solutions have different height, so that this bottom cannot be zero and lambda can be well defined. Most common choices for Z1 and Z2 are here. Z1 is 0 and Z2 is 1. So one is shooting flat and the other one is shooting along with a 45-degree angle, like in this figure. Okay, now we have a summary for the linear shooting method. To solve the boundary value problem, we first solve two initial value problems, so that in fact there is not boundary value problem, it must be initial value problems. Now one is, now y double prime is given this way, this is linear over there, and y at alpha a is alpha, and y the slope is 0. Now only the difference for y2 is slope is now 1. So we shoot twice, and then after getting the solutions, we try to get lambda. Because the slopes are different, the solutions are different, and then from this claim theory, we know that y1b cannot be the same as y2b. So we can find the lambda, and then along with this lambda, we can get the final solution. This is desired solution, y. And of course, this y will satisfy that one here, y at b is beta. Right? Okay, we have a remark. Now, once we try to solve this second order ordinary differential equations, then we may try to use some standard solutions solving for only first order differential equations. In order to do that, we may introduce extra variable. For example, y prime is u. We introduce this new variable, then u prime is the same as y double prime, so that we have that. Now y prime is u, so we can write in this way. So rather than second order equation, we consider a system of first order equations, and y prime equal u, u prime is this right side. Here, remember, look at this one. Right side has no derivative involved. And left hand side, we have only first order derivative, so that we can use one of the standard ODE solver. That was considered in the first part of numerical analysis. Also, you may try to see some video clips addressing this issue. Okay, for solving this problem, now here we may consider the fourth order Runge-Kutta method, RK4, that is formulated in this way. Each step, after partitioning the interval, and in each step, step by step, we are try to get the value at due step, due point, from the earlier point value, and the next point we can get the value in this way. And this is now right side, 4 evaluations, K1, K2, K3, K4, defined in this way. Now, linear combination, total contribution is 6, 1, 2, 2, 1, divided by 6. So in a sense, right side, that one is average slope, representing this portion, and average slope n times h is update to get the value on the next point. That's the fourth order Runge-Kutta method. For this one, locally, error, truncation error is order 5, h to 5. So the global error becomes order 4. So it's quite accurate. Let's see the code. For RK4 system, I implemented this one in Maple, and along with some initial opening, look at over there. For F, now evaluation first, and now at midpoint, HH is half H, so that in midpoint it is evaluate by using K2 again. Now at the same point is evaluate, and at the last point, at the right point, now one more evaluated, and this linear combination, and times h over 6, and update for the next step. That's an implementation in Maple. Okay, let's try to solve this second order equation, and that is now initial value problem. And at 0, the value and slope is given. And for this one, we are introducing a new variable, and to be y prime, then u prime must be here. From this one, after moving this one to right side, we have that. And now y at 0 is minus 0.4, and that is u prime. Okay, y prime, which is u at 0 is minus 0.6. So that this is a system of two first order differential equations. For that one, now rather than u, here the variable is used to yp, and look at over there. So that is now, that is yp, y prime, and then this one is that one. Okay. And x and y, yp. And we defined this one so that the variable, because the maple will work with symbolic computation, so that we have to give information x, y, yp are symbolic variables. This is the initial value, and from a to b, 0 to 1, and number of the subinterval is 10. Now we solve it by using the algorithm RK4 system, and also by using here desolve, we try to find the exact solution. That is now the exact solution, and along with this one, we can measure the difference and error. Now, yn, y sub n is y value, computed value at xn. Y at xn is exact value, and y prime, yn is now here yp at xn, computed value. This is exact y prime. And error can be found from here to there. That is error for y. Now, from these two, we can find error for y prime. As we can see, the error is order of 10 to the minus 6 for both y and y prime, even though we chose only 10 points between 0 and 1. It's a fourth order scheme, so that is quite accurate. Now, we go back to the boundary value problem from 1 to 2. At 1, the value is 0. At 2, value is 2. And we have a second order linear differential equation. For this one, again, by using the RK method, so that we try to make each one, for each one, now introduce yp, and then we try to make right side. Okay. Here, and from 1 to 2, and alpha is 0, and now beta is 2, and here n is 5, and we try to solve the problem twice. And in the beginning, along with 5 subinterval, and next along with 10 subintervals. And for each time, we solve the problem in like initial value problem, alpha is 0, and slope is 0, and second time we solve along with alpha and slope 1, and now result will be here y1 and y2. From y1, y2, we try to get lambda, and linear combination of lambda will make the final solution. For each nt, and so that which will be 5 and 10, we get this solution. And along with the exact solution, we can measure the error. Okay, let's look at the result. Okay, from 1 to 2, and when h is 1 over 5, then these are computed solutions. We measure the error from the exact solution. So we have error here. Now when h is 1 over 10, now the computed solution at those points are here, and error is measured again from the exact solution. So as you can see here now, the solution is way better. In fact, this solver is fourth order scheme, so theoretically the error here is 16 times smaller from here. As you can see, it's really almost 16 times. So that once you choose 10 points, then now you can see here error is order of 10 to the minus 5. So quite accurately you can solve the problem. Okay, that's the end of section. Thank you.